Okay, so the next section we'll be talking about is section 4.3. In section 4.3, we'll be talking about logarithmic functions. Now, it's important that you understand what a logarithm is, like what its purpose is. So let's talk about inverses. The inverse of adding is subtraction. So like if you had a problem x plus 2 is 5, you would subtract to solve that. The inverse of multiplying, of course, is dividing. So 2 times x is 8. Of course, you would divide to solve that. The inverse of square rooting is squaring. So if you had the square root of x is equal to like 2, you'd square both sides to get that. But what if we had a problem where it was 2 to the x power is equal to 5? Now you can't write 5 as 2 to a power, so that's why we have to use a logarithm. The inverse of an exponential is a logarithm. That's its purpose. So I'll even write that again. A logarithm is the inverse of an exponential function. One property that we're going to be using, there's a lot of properties with logs, but one property we're going to be using right away is called the translation property. Now the translation property says if you have a problem like, say it's x is equal to a to the y power, we should be able to convert this into logs, where we could write log base a of x is equal to y. Notice these numbers are our bases. These numbers are exponents. And x is considered an argument. Argument just means what you put into a log. Now a couple things I just want to point out. The base of the log can't be 1 and it has to be greater than 0. Also, when you're taking the log of something, just like a radical, you can't take the square root of a negative number, right? Same thing with the log. The argument has to be greater than 0. So let's take a look at some problems where we'd be using the translation property. So let's solve logarithmic equations. So the main idea with this is sometimes when people get stuck, it's always a good idea to try to translate first. So for example, a problem like this, log base x of 8 over 27 is equal to 3. Look at your translation property. Right? So we have it in logarithmic form. Let's write it in exponential form. One way that I remember this is I think about a crisscross. So like x to the third is equal to 8 over 27. And then once it's converted, you could just easily take the third root. And you just get x is equal to 2/3. The way that this is read, just by the way, so everyone knows, we read this log base x of 8 over 27 is 3. How about if we had log base 4 of x is equal to 5/2. Well, this means 4 to the 5/2 power is equal to x. I just use our translation property, a little crisscross. So this means the square root of 4 to the 5th power is equal to x. Square root of 4 is 2. 2 to the 5th power is 32. 2 to the 3rd is 8. 2 to the 4th is 16. 2 to the 5th is 32. Last type of problem like this, what if we had log base 49 of the cubed root of 7 is equal to x? Let's use the translation property. 49 to the x power is equal to the cubed root of 7. Let's try to get the same base, right? Remember, that's how we solve exponential equations. 49 is just 7 squared. And the cubed root of 7 to the first is really just 7 to the 1/3. So power to a power means we multiply. 7 to the 2x is equal to 7 to the 1/3. And we could set the exponents equal. 2x is equal to 1/3. And if we divide by 2 or multiply by 1/2, the reciprocal, we get x is equal to 1/6. Next, let's talk about how to graph a logarithmic equation. So when we're talking about graphing, let's recall what we talked about the exponential graph. Remember, an exponential function looked like this. This is the graph of, let's say, y is equal to 2 to the x. And we said there were 3 things you need to know about this. One is its shape. Shape looks like a hockey stick. Second one is the y-intercept is equal to 0. The third one is a horizontal asymptote is y is equal to 0. So if we're going to graph its inverse, remember logs and exponential functions are inverses, what we could do is we could just reflect it over the line y equals x. So let's talk about what that would look like. Y equals x is a 45-degree line going through the origin. And remember, the way that we graphed is we just switched the x and y values, right? So this point right here, that's at 0, 1, would reflect and be at 1, 0. All right, they're working on the grass outside, so I hope that's not too distracting. And then if we take the point, like let's say when x is 3, 3, 8 would be like over here. And we reflect it, that would be 8, 3. The horizontal asymptote, that was y equals 0. If we reflect that, so instead of y we use x equals 0, we get something that looks like this. And our graph for the log would look like this. Okay? So that's what the graph of log would look like. So we could actually even label this y is equal to the log base 2 of x. If it was log base 3 of x, it would just be a little bit steeper, but it's not necessary that you know that. So just know for a log graph, one shape is, it still looks like a hockey stick, maybe just lying down. It doesn't have a y-intercept, but it has an x-intercept of 1. And I think over here I said the y-intercept was 0, but that's not true. It's just a little mistake, so I'll fix that in the notes over here quickly. And the third thing about the log graph is that it has a vertical asymptote when x is equal to 0. So it's important that you know those different shapes. So let's try graphing these. So let's graph. Y is equal to the log of, make up any number, let's say 4x. So it's a pretty easy graph. Just review what we did before. So we're not moving it left and right? And remember with log, we still have the same transformation. So we can have a times the log base like 2 of bx plus c, and then plus d. But really, the only kind of transformations we use with logs is we go left and right, and we go up and down. This graph, we're not adding or subtracting anything, so it's just a basic log graph. It would look like this. One thing is our hockey stick. Second thing is our x-intercept is at 1. And our vertical asymptote is at x equals 0. Now the domain for this graph, you can plug in any x value you want as long as it's greater than 0. So we're going to start at 0 and go up to infinity. And our range, the lowest it goes is negative infinity, and it's going to keep going up for forever. So that would be how we graph log base 4 of x. Let's translate that a little bit. What if I asked you to graph y is equal to log base 3 of x plus 1? We always start with the parent graph. This is what the parent graph looks like. Now 3 would be a little more steep. The steepness doesn't make a difference to me as long as it looks like a hockey stick. But we do have that plus 1 on the inside. So when you have a plus 1 on the inside, that actually moves to the left 1 unit. Anytime you have a graph and you put plus 1 on the inside, it goes to the left 1. So a few things I'm looking for here. Our hockey stick shape. Then we also, the x-intercept wouldn't be 1 anymore. Think about it. We went to the left 1, right? So on a number line, if you were at 1 and then you go to the left 1, the new x-intercept is going to be 0. And you could see that from looking at the graph. And our vertical asymptote, well, the graph got shifted, right? So the vertical asymptote was at 0, but we're going to the left 1. So now the vertical asymptote would actually be at negative 1. As far as our domain here, domain is, well, we can't have this be 0, right? So if x plus 1 is equal to 0, x has to be bigger than negative 1. We could plug in any number from negative 1, not including negative 1, so like bigger than negative 1, up to negative 1, up until infinity. And our range, looking at the graph, would go from negative infinity to positive infinity. All right, one more graph I wanted to talk about. We'll move on to some more interesting things here. Let's say we had y is equal to the log base 3 of x minus 1 and then plus 2. So this graph's going to the right 1 and up 2. Start with your parent graph. That crosses the x-axis at 1. But now, on a number line, think about it. If you're moving to the right 1, the x-intercept was 1, right? You're moving to the right 1. So now the x-intercept is going to be 2. And the vertical asymptote, normally at 0, but if you're moving 0 to the right 1, it's going to be 1 now. And we still have our hockey stick shape. And for our domain, actually, you know what? I forgot about the 2. We're going to have to move this graph actually up 2. So 1, 2. And it's a little bit unsure of now how to get the x-intercept. I forgot about that +2 there. So we'll learn in the next section how to figure that out. But our vertical asymptote is still 1. We moved it to the right one, so normally it's at 0. And that's what the graph would look like. Right? So we moved it to the right one and then up 2. The domain, well, the inside of a log can't be 0. So x minus 1 is 0. So you can't plug in 1, but you could plug in anything bigger than that up until infinity. And our range, looking at the graph, it goes down for forever, and it's going to go up for forever too. So that's how we graph using logs. Let's talk about some more properties of logs. Okay, so I actually have a few here. One of them we already talked about is the translation property. Translation property says that if we have log base a of x is equal to y, remember we do our crisscross and the exponential form would be a to the y power is equal to x. Second property is the inverse property, and this is huge because it's going to allow us to solve exponential equations. The inverse property says if you're taking the log with the same base of an exponential with the same base, they actually cancel out. That's huge. Now, in the exponential form, if you have an exponential function of a log with the same base, they would cancel out too. Exponential functions and logarithmic functions are inverses. They cancel each other out, so that's what that would look like. And we'll see examples with this soon. Third property is called the product property. Product property says that if you have two logs, so let's call it log base a of m plus log base b of n, you could actually multiply their arguments and combine the logs. So two logs separated by a plus sign, we can combine them by just multiplying their arguments. The exponential property that that's similar to is if you had like a to the m power times a to the n, if the same bases, you would actually add their exponents. So there is some similarity between logs and exponents. Similarly, we have a quotient property. Quotient property says that if you have logs separated by a minus sign, that's the same thing as dividing the arguments. You can combine them as division. Using the exponential reference, if you're dividing with the same base, we know that we could subtract those. And then the last property is the power property. Power property is pretty cool. It shows you that if you're multiplying the outside of a log by a number, you could actually make that into an exponent. Like that. So if you have 2 times the log of something, you could actually make that 2 into an exponent of 2. Another way to think about it is sometimes it's better if you have an exponent. You could bring that down and turn it into multiplication, but we're going to see examples of this. So let's use some of these properties. Use properties of logs to fully expand. And I'll give you some examples. So we're looking to make this as long and drawn out as possible, just to practice using our properties. So what if we had log base 6 of 7 times 9? Well, we could use the product property, and if there's multiplication inside, we could actually write this as log base 6 of 7 plus the log base 6 of 9. That's using the product property. What about if we had the log base 2 of the cubed root of m squared? Well, log doesn't really get along well with radicals. We always want to use logs with exponents. So let's convert that cubed root to a power, m to the 2/3. Then we could use the power property and bring that in front. So we could write 2/3 times the log base 2 of m. That's using the power property. What about if we had the log base a of mnq divided by p squared t to the 4th? Okay, well that's a quotient, so let's go step by step. This would be the log base a of the top, mnq, minus the log base a of p squared t to the 4th. That's using the quotient property. Okay, so our next step is we could actually use the product property here and here. So this would give us the log base a of m plus the log base a of n plus the log base a of q minus the log base a of p squared plus the log base a of t to the 4th. So that's using a combination of the quotient and product property, but we could even bring these numbers in front using the power property. And all I did here is I just distributed that negative in, right? Because remember, this is going to use the product property, but you're subtracting that whole thing. Let's do one more of this. What if we had the log base b of the nth root of x to the 3rd, y to the 5th, divided by zm? First thing let's do is let's convert that radical to a power. And we could bring that power down. Well, now we have a quotient property. So let's write 1 over n times the log of x to the 3rd, y to the 5th, minus the log base b of zm. And then we could finish this using a product property and then a quotient product property and then a power property. So right here we use the power property. Right here we use the quotient property. And now we're going to have 1 over n times log base b of x to the third plus log base b of y to the fifth minus log base b of z plus log base b of m. Now we could bring these powers down using the power property, and let's see what this is fully expanded. This would be 1 over n times 3 log base b of x plus 1 over n times 5 log base b of y minus log base b of z minus, distributing this negative here, log base b of m. And then if you wanted to, you could write this 3 over n log base b of x plus 5 over x, or 5 over n, I'm sorry, log base b of y minus log base b of z minus log base b of m. All right, so hopefully by now you get the properties of logs. That's fully expanded though. So let's go the other way. Let's contract them. So let's write as a single log 2 times the log base a of m minus 3 times the log base a of n. Okay, well I see a quotient property and a power property, but we can't use the quotient if there's numbers in front. So let's bring these numbers as a power first. This is log base a of m to the second minus log base a of n to the third. Well, that's using the power property. Now let's use the quotient property. Log base a of m squared divided by n to the third. And we'll do one more, like this. What if we had 5 times the log of a times z plus 7 plus the log of a times 2z plus 9. Well, we can't combine anything until we get nothing in front of log. So let's bring that 5 up using the power property. Would be the log base a of z plus 7 to the 5th power plus log base a of 2z plus 9. And now that there's nothing in front of our logs, we could combine those two using the product property. So we'll write log base a of z plus 7 to the 5th power times 2z plus 9. So I'm not going to actually distribute that. The whole purpose of this here is that we're just getting practice using our different properties of logs. And we got this by using the product property. Last example for this section. These are fun. They're like a big puzzle. Given the log base 10 of 2 is equal to 0.3010 and the log base 10 of 3 is equal to 0. That 0 is not too good. 0.4771. Find the log base 10 of 6. So the way this works is we have to use a combination of 10, 2, and 3 to figure out how to get 6. Well, I mean, this one's pretty easy. This is just the log base 10. 6 is just 2 times 3, right? So using the product property, we could write this log base 10 of 2 plus the log base 10 of 3. And we know what those are because they're up here. Log base 10 of 2 is just 0.310. Log base 10 of 3 is just 0.4771. So if we just add those two together, 0.3010 plus 0.4771, that comes out to 0.7781. That's how we do a problem like this. We'll do one more, maybe a little bit harder. What if we wanted to find the log base 10 of 18? So think about, how can you get 18 from 10, 2, or 3? So right away I'm thinking that 18 is the same thing as 9 times 2. We have 2, right, from the log base 10 of 2, but how do we get 9? Well, that's really just 3 squared, right? So let's use our properties. This would be log base 10 of 3 squared plus the log base 10 of 2. That's using the product property. So we could bring this 2 down. So it's 2 times whatever the log base 10 of 3 is, plus the log base 10 of 2. Well, I know what the log base 10 of 3 is. Log base 10 of 3 is 0.4771. And I know log base 10 of 2. That's 0.3010. So if we just type this in our calculator, we should get the right answer. 2 times 0.4771 plus 0.3010. That comes out to 1.2552. And that's actually the same answer you would get. Instead of doing it like this, we could have also said the log base 10 of 3 times 3 times 2. That would have given us the same answer. This would have been the log base 10 of 3 plus the log base 10 of 3 plus the log base 10 of 2, which is 0.4771 plus 0.4771 plus 0.3010, and that's exactly the same answer.